Hello, everyone, and thanks for joining our seminar series from DSRC Center. And definitely, I would say that, our speaker doesn't require any formal introduction. Those who are into this, they know who is he. But I would still go by the tradition to welcome Professor Mathias Payer, and we really thank him for his time, and he agreed on giving this seminar. And he's a professor at the EPFL, and before that he was in Purdue University, and he spent time in Berkeley as a postdoc with a group of Don Song in Blaise group. In fact, I remember with Blaise because at the time when it was formally she presented the paper, I was there in that conference. I just finished my PhD, and it was very nice at the time, like in 2012, I think, or something. No, 2008, something. And it was really ahead of time at the time, like big Blaise platform. It was very nice. And yes, and as far as Professor Mathias is concerned, I would say that he has worked on various hardcore problems of systems and software security, starting from control flow integrity and seminal work on code pointer integrity. And I followed a lot. I think last decade was dedicated to control flow integrity. There were so many things in control flow integrity, and he really contributed a lot in that direction. And then, of course, his current focus is on maybe fuzzing and then sanitization and hardening software. So we will hear from him his experience and his suggestions on one of the most hot topic, fuzzing and then crash. So up to you, Professor Payer.
Thank you very much, Sanjay. This was very lovely. I hope I can live up to the expectations, and we'll see how far we get. I will talk about. Let me try to share my screen first, and just to say it as well. I would have loved to actually be there in person. I much prefer on-site talks because they are usually much more lively and allow for much more interaction. Having said that, if you do have a question, please feel free to interrupt me. I don't know how this seminar or the webinar is being set up. I usually, if I have multiple screens, I try to monitor the questions at the same time. In this setup here, I only have a single screen. So as soon as I go full screen on the slides, I will not be able to see the questions. So if somebody in the room, maybe Sanjay or one of the other people there, can relay the questions and just interrupt, I would be happy to answer questions as we go along. It'll be perfect. So without further ado, let's get started and let's talk about some of the recent fun fuzzing work that we've been working on. Again, thanks Sanjay for the lovely introduction. This has been a super nice journey. We actually completed, you said 2008 you completed your PhD. I was only a couple of years afterwards, so you're still a couple of years ahead here, but it's interesting to see other journeys as well. So today I will talk about fuzzing for profits and how we can turn crashes into vulnerabilities. And this has been a fun journey, and I invite all of you along onto this journey. Join the fuzz train or the fuzz hype train. Jump on the train and let's see how far we can ride. Of course, this is not possible on my own. A lot of the research here has been done in collaboration with a lot of great and amazing people, some of which I was very happy and very lucky to advise during their PhDs and to join me in my research group, and us working all together collaboratively on very interesting different topics. Sanjay already hinted at this a bit. There's three main areas in systems security that we are working on. Only one of which is software testing. And I kind of group system security into these three major areas, and I'm interested in researching all three of them. And maybe like if there's questions afterwards, we can follow up on those in a bit more detail as well. So software testing is you have a piece of software and you're trying to get rid of all the bugs. And this is more the laboratory setting approach where you're observing, figuring out how components are interconnected, find kind of vulnerable inputs, detect them, and get rid of them. So fuzzing is a key technique that has gained a lot of momentum recently that discovers a lot of these vulnerabilities. And sanitization is a complementary technique that allows you to actually find these detected vulnerabilities as they're being triggered. Getting rid of bugs is best, so this makes your software more secure. If you cannot get rid of all the bugs, and given the complexity of current code, there's always a second step that you need to take, or second line of defense. And this is where mitigations come in. And mitigations pretty much, they stop exploitation and form a last line of defense. And here we've worked on things like control flow integrity, type-aware data guards, and so on. So in the end, mitigations are like, it's a best effort. They're not complete. They're not going to stop every single attack. Like the bouncer I show in the picture, he's not going to stop every single attack, but they're going to make it harder for somebody to exploit them. Finally, a more evolving, well, if there are people there that did security in the 80s, they will say not evolving, but something that has long existed and hasn't received enough attention. But the third area is to break large and complex systems into smaller trust domains. Breaking existing systems into compartments is an interesting approach, allows you to enforce a principle of least privilege and protect against severe attacks and reducing the privileges of individual code. So it's an interesting angle that we're going to see much more of in the future, and we'll see how far we can push it there. In the end, we'll need all three parts of system security to make systems more secure going forward. And as said, like all that I'm presenting here has been done in collaboration with a lot of amazing folks, and I want to give all the credit I can to my students that have been instrumental in actually coming up with the ideas, design, implementations, and working through it. So I greatly appreciate all these great people I've been able to work with. So let's dive in and see what this is all about. Now, if you've recently attended top-tier conferences, I'm speaking about Oakland, Usenix Security, CCS, NDSS, all of them have something in common, and even the other conferences as well. If you look at the sessions, they all have, like in the program, they all have individual sessions on fuzzing. So fuzzing is the thing that started with maybe like a paper or so in 2016 per conference, 17, 18. And now there's several sessions at each of the top tier papers that are just focusing on fuzzing, right? So NDSS, Usenix Security, Oakland, RAID, and so on. And you may be wondering, what is all the fuzz about? Why is this so important? Why has this received so much attention? Finding bugs has been a topic in software engineering for a very long time. But with the explosion of fuzzing, it has become a key security technique to find and fix exploitable bugs. Right? So this is a new and different angle that allows us to find bugs that could be of uttermost importance to an attacker, allowing us to detect those bugs and to actually fix the code that is vulnerable. There's bugs, and bugs are everywhere. It's all the code that you'll be running on your system, like any complex system, will have bugs in there. And fuzzing allows us to find and trigger many of those bugs to further secure the software and make it less likely to be exploited in the future. Many of the bugs on our systems are exploitable, can be used as a stepping stone, either by themselves or in combination of other bugs. And bugs and exploits and vulnerabilities can have many different facets. So it could be just could be used to simply install malware on your system, could be used to exploit from virtual machine to the hypervisor and taking over the the host machine. It could be used to turn your smart car into a remotely controlled toy vehicle being driven into a ditch. It could invade your physical spaces by attacking smart embedded systems, vulnerabilities in those, or could be used to spy on you by taking control of cameras. So as you very likely will agree, in increasing the security of all these devices to protect your data, protect your assets, and protect your physical space is of uttermost importance. What should you do? There's two approaches in software security. You can do prevention or mitigation. Ideally, you'll spend as much resources as you can on prevention to remove as many bugs as possible. So software testing gets rid of bugs ahead of time. And as you may know, only a fixed bug is a good bug, right? So you want to figure as many bugs as possible, getting rid of them to fully stop any form of exploitations. So fuzzers explore the programs and sanitizers then detect the bugs. And I will get into more detail for both of those topics. On the other hand, mitigations will run at runtime and add some additional form of insurance that for any bugs that you may have missed, you can actually make sure that the exploitation of those bugs is much harder. So mitigations may hinder information leaks, make code execution harder, and simply make exploitation overall as a technique much harder. Now, a reason for the rise of fuzzing may be because we have reached a level of mitigations that makes it reasonably hard for the attacker to achieve anything. So we can now move to a best effort basis on finding as many bugs as possible. So these two best effort mechanisms, finding as many bugs as possible, while we'll never be able to find all bugs, and mitigating and making it as hard as possible to exploit remaining bugs, together massively increase the security of our software. We will never get complete security. We'll never find all the bugs, most likely because code is being added much more faster that can be tested in practice. But it's simply the code is too complex, and the complete techniques like symbolic execution, formal verification, bounded model checking, and so on likely do not scale to the massive amount of software complexity that we have on our systems. If you've ever tried to compile Chrome, you will see the massive amount of complexity that is in there. So Chrome and the support system around it clock in at about 100 million lines of code. Now, if you, 100 million lines of code are very, very hard to imagine or to visualize. That's why I have a picture here of an amazing computer scientist, Margaret Hamilton, with the code for the Apollo guidance computer. So this thing flew to the moon, and it was written in a very clunky assembly dialect, and it clocks in, if you are generous, at about 2 meters of complexity, including all the documentation for it, right? If you print out the source code of Google Chrome, you end up with a stack of 370 meters. So it's like 2 meters versus a skyscraper. Maybe not a skyscraper in Dubai, but a regular sized skyscraper, right? So this is a massive order of increase in complexity. So we're like at least 2 orders of magnitude off, even though this is written in a high level language, right? So this is a massive amount of complexity that is incredibly hard to imagine and visualize. And bugs may connect a lot of the different components across these different layers, making it very hard to connect and analyze. This is where fuzzing comes in. Fuzzing is best effort. We don't even try to be complete. Fuzzing simply tries to find as many bugs as quickly as possible. And fuzzing is very simple, right? You have a binary. Here we call this the test me binary, and then you throw some input at it. So you have your shell, you type test me help, it says usage, test me, and then a 32-bit integer argument. Test me AAA says please enter an integer. So to write a fuzzer for this, we do just a while loop. We throw in 4 random bytes and run our binary with this test input. And this is what fuzzing basically is. You just throw input at it as quickly as you can generate it and observe if it crashes. If it crashes, you store the input and write it to a log file. And the key idea of fuzzing is to be as fast as possible. Now, let's expand this a bit, right? And talk a bit more about fuzzing in a bit more detail. We have a program, a target program, that is the program under test. The fuzzer creates some input and runs the program with this input. So it's an automated framework that on one hand generates inputs, on the other hand executes this input under the program. If the program crashes, the fuzzer stores the input in a crash log and says, yay, we found a new crash. All is good, right? We found a bug. And the fuzzer repeats this until you run out of cycles, right? So a fuzzing process will consume as many cycles as you give it, compared to symbolic execution or bounded model checking that may complete. Well, in theory may complete, but in practice will, due to state explosion, will always run out of cycles as well. So fuzzing keeps iterating, keeps creating new inputs, runs the program pretty much forever. To make fuzzing a little bit more precise, we have developed coverage maps or like an observation of which parts of the code have been executed. You can imagine this as some form of map or some form of, map is a good abstraction that tells you which areas you have already visited. And you just note on your map that, hey, these areas have been covered. This is why it's called a coverage map, right? So the fuzzer keeps track of the map, and whenever a program triggers new coverage, it can further use this input as an additional input to mutation. So instead of always creating new input based on a single baseline, we can now have multiple inputs or multiple starting seeds to create new targets inputs to hopefully create and discover new areas in the program and find more and better crashes going forward. To make fuzzing effective, we need to observe three requirements. First, test cases must trigger bugs, and to find test cases that do trigger bugs, we have to be effective. So we have to have a good feedback, and this is where coverage comes in. And I'll talk more about that in a bit. Second, the fuzzer must be able to detect bugs. This is where sanitization comes in, and performance is key. And I think it took me way too long to realize the third challenge or the third observation. It's a zero-sum game, right? You have fuzzing, the basic assumption of fuzzing is you have a finite amount of cycles. You want to find as many bugs as possible given this finite amount of cycles. Any cycle you spend on analysis, you don't spend creating a new input to trigger any kind of alternate vulnerability. So it's a trade-off, which as a systems person is super interesting to me because we can optimize it, we can move, we can shift, we can try to reallocate, and this is what makes fuzzing so interesting for me as a research topic. Let's look at the first challenge, tracking coverage, and figuring out how we can test and track coverage more effectively. Most fuzzers have moved to some form of edge coverage, where individual edges on the right-hand side, I show a simple control flow graph, are instrumented and can then be collected during execution. So this instrumentation is added by the compiler and will simply increment individual coverage items in the coverage map. Coverage can measure the different parts of executed programs. It could be at the granularity of functions, basic blocks, line or statements, edges, pass coverage, and data flow coverage. Ideally, we would get full pass coverage and data flow coverage, but the collection of those is very complex because the execution pass or the data flow through a program can be arbitrarily complex. So execution paths can be extremely long and would require a lot of input and would be very hard to work with because they're also very challenging to compare. So it's not immediately obvious if you can compare pass 1 to pass 2. Like there's an equivalence check, yes, but relations between paths are very hard to calculate. This is why most fuzzers have settled on edge coverage with some additional benefits to it. And edge coverage is a great trade-off between cost, complexity, and precision. So edge coverage means that whenever like the compiler instruments all the different edges from one to another basic block to increment a counter in the local coverage map. the fuzzer then reads out this counter to add it to their to the global coverage information. So fuzzers collect coverage and have a notion of global coverage, and this can be a simple array that is the same length as the coverage array in the program itself. A simple approach is to simply collect the highest most bit that was set for each of the edge counts. And here in this example, we see that this backward edge here has been executed at least 4 times, the third bit being set. If we now collect a new execution, we have an input that we have generated, we see that we execute this backward edge 7 times. The topmost bit of 7 is 4, so we do not increase. We do not store this seed for further mutation because it is not interesting to us, and we would throw it away. Now, instead, if the fuzzer creates a seed that triggers 8 executions, so this loop is executed 8 times, we would assume that this is interesting because the topmost bit in the global coverage has changed, and the fuzzer would keep this seed, the seed that created this new input, for further mutation. And this allows us, because like it has been a new area of code has been triggered or has been executed a higher number of times than before, then we know that, hey, this is actually interesting. This is something that that makes sense to look at further. And this is how the fuzzer keeps track of the different program areas that are being explored. Now, looking back at fuzzing, you may remember EPFL, which was introduced in 2013. And this is the first fuzzer that actually made fuzzing extremely viable on a larger scale. This was released by Google Project Zero, and then resulted in a massive amount of research happening on top of EPFL. I call this the Cambrian explosion of fuzzing. So it's with EPFL, it took off. It was the right set of constraints. The Cyber Grant Challenge, the DARPA Cyber Grant Challenge just happened. It was an extremely exciting area about automated analysis of code. And people got interested in finding and fixing as many bugs as possible. And EPFL led to this explosion of other fuzzers that explored a lot of other different areas, such as by adding different coverage metrics, by adding different mutations, by adding better input scheduling, by adding constraint tracking, and so on. And since then, we have seen, I think the last survey we did, we are at about 60, 70 papers that all follow up on EPFL. And it's just crazy how the field is developing and exploring all the different parts and how to make fuzzing more efficient and fuzzing better. The coverage metrics we have looked at, they can be more precise on the control flow level or on the data flow level. And both dimensions are interesting. On the control flow level, we have reached an somewhat agreement that edge coverage is likely going to be good enough, with some context sensitivity being added in on demand. A second dimension that is now being explored more and more is towards data flow. Can we, for example, extract information about memory accesses, comparison operators, a little bit of data flow analysis, and then add this in addition to other metrics to inform the fuzzer about how the program state space has been explored and how the different parts connect together, giving the fuzzer a little bit more insight to distinguish similar but not exactly similar cases, to give it a little bit of a leeway. All under the assumption that it must be the cycles must be used very, very sparingly, allowing it to still generate enough input and explore enough of the state space. So coverage, to summarize the first challenge, tracking coverage is important. Coverage helps the fuzzer to effectively explore new code areas and allows the fuzzer to keep track of what code areas have been analyzed so far. Edge coverage is cheap to obtain and precise enough, sometimes augmented with additional bits and pieces for context sensitivity and potentially data flow. What we found is there's a surprising large amount of flavors of different coverage with very subtle differences. So it's very hard to tease those apart and actually figure out what the benefits of these different systems are. And it's also very, very hard and challenging to classify them. Future research that I'm very much interested in are alternatives to code coverage. Like instead of code coverage, what else can we use to infer something that gives us that tells us, hey, this input has reached some new behaviors and new interaction. Combining different coverages at the same time, or adjusting the coverage as needed. So, for example, we may not always need the most fine-grained coverage collection throughout all the code and throughout all the time, right? Through both space and time. So we want to adjust granularity in space and time, so that sometimes we get more fine granular, or for some functions we get more fine granular. These are interesting areas of research. Are there any questions so far that I can answer?
Yeah, I have one question. In the previous slide, so you talk about the genealogy of fuzzers, the one before, and so you speak specifically about gray box fuzzers. Why?
Why I focus on gray box fuzzers? They are the most effective fuzzers so far. There's been a whole bunch of other fuzzers that I could have compared as well. There's mutational fuzzers, generational fuzzers, gray box, white box. If I would speak about all the other types of fuzzers, I would only speak about the different types of fuzzers, and there's a whole bunch of other material. There's been a couple of other fuzzers before. All of them are interesting. Gray box fuzzers are the only type of fuzzers that have seen such a massive explosion. And if you look at bug counts, discover bugs, if you look at syscaller, if you look at the results from Kostya Serebriani, who recently talked about their fuzzing efforts inside Google, there's tens of thousands of bugs found through gray box fuzzing. That's why I focus on those. Does that answer your question?
Yeah, exactly. Sure. Thank you.
I hope I didn't offend you because you're a symbolic execution expert.
No, it's fine. It's just the genealogy starts in like 2013, and
right,
I was just wondering.
Yeah, it's a gray box genealogy. It started as AFL pretty much, right? So there's been stuff before, right? But I had to start, like, otherwise it gets too long and it doesn't fit on a slide. I'm with you there. Cool. Let's continue if there's no more questions. Cool. Let's talk about detecting bugs, right? It's a great first step if you reach the buggy code. It's even better if you trigger the bug, and it's best if you actually detect that the bug has been triggered, right? So we need an oracle, and on the lower right, I'm showing the oracle of Delphi, who has one of her visions to detect and projections, right? Different types of bugs require different oracles. If you don't have source code, this is challenging. You may YOLO it and simply rely on segmentation faults, but this is not very complete. One option that is being explored is to statically rewrite or even dynamically rewrite the binaries, but this usually comes at a rather high cost. If you're interested in binary-only fuzzing, we are working on some techniques there, and I can talk about that more. But that's an interesting area. Memory safety, use address sanitizer. Concurrency issues, use a thread sanitizer. If you want to detect type safety violations, use a type sanitizer. If you want to find logic bugs, well, best of luck to you. There's no sanitizer for that that exists. And that also hints at an interesting research area that could be done here. If you look at, I don't know, like if I would be there in person, I would ask who has run fuzzing campaigns already, and I would hope many hands go up. So I'll just assume that some of you have been running fuzzing campaigns before. And what you may have observed is that, yeah, crashes are great, but bugs are, it's hard to turn them into bugs. And here in this example, in the screenshot, we have American Fuzzy Lob running on an image decoding for 2 minutes. And you see in red that we found a total of 7,089 crashing seeds and 124 unique crashes. How many, like AFL has decided, or AFL tells us, it found 7,089 inputs that trigger a crash. And it tells us that 124 of these crashes are unique and are likely 124 different bugs. Now, in reality, they are all due to the same bug. So this is a single bug that is triggering all these crashes. And this vastly pollutes the search space of the fuzzer. So a fuzzing campaign that runs for sufficiently long produces n crashes or n crashing seeds that map to n bugs. And n is larger or equal to m. Now, in practice, as we have observed, n is usually orders of magnitude larger due to many different paths that can be taken to the bug or inputs to the bug. Now, given that we have n crashing seeds, how do we distill those many crashing seeds into the n bugs that we are looking for? And this is exactly something where that is the most costly aspect of bug analysis at this point in time, right? This is where you have to invest developer time. You run your fuzzing campaign, the fuzzer gives you n crashes, and right now you would have to go as an analyst, you would have to go through all of these n crashes one by one and triage them and figure out what bug they are, fix the bug, analyze it, and then go on to the next one. So this is extremely time consuming and extremely slow. So you could do crash grouping based on call stacks, right? So you have the n seeds. First idea, just look at the call stacks. Group crashes based on a hash of the top k stack frames. This results in a lot of type 1 errors. So there are duplicate bugs that crash at different locations. It's the same bug that is counted multiple times, but if it crashes at different locations, you will count it multiple times. So the CV here, where the V pointer points an illegal address, will count as 3 different bugs. One's for U short, one's for U long, and one's for signed short values. Right? So this is not a viable solution because we overcount the number of bugs. It still results in too much work. Second option is let's just count the crash location. Well, there's also type 2 errors in addition to type 1 error. Just recording the crash location itself is not enough. So for example, there could be bugs that, like if you have an overflow in the mem copy, we could have crashes at from 2 different locations that then result in a single bug, and we lose context of the other bugs. So here we have 2 crashes in mem copy, but it would be two different bugs. But we would only record the crash in mem copy as a simplified example. So this would undercount the number of bugs. So we have both false positives and false negatives using these existing locations. Can we do better than that? We've looked at our corpus where we did 59 CPU years of fuzzing. So this is quite substantial. And we discovered 254,000 crashing seeds. The existing grouping mechanisms both over and under approximate the number of bugs. So neither of them is effective. What we found though is that each bug is triggerable by a unique trigger, a unique path. So if you think about it, if you imagine or visualize a bug, there's a unique bug trigger that identifies the single bug. If there would be multiple triggers, then these would be multiple bugs. So each bug can be distilled into a small sequence of instructions on the path to the crash. It may not be immediately before the path, but there's a short set of instructions that uniquely identify a bug. Large sections on the execution path to the crash are irrelevant. So you have to figure out which subset of the path actually conforms to this crash trigger or to this bug trigger. And the last observation we had is that there's some similarity in the control flow graph topology that would enable grouping of similar bugs. And I will talk more about this in a bit. Our idea is that we want to minimize paths, right? The underlying assumption is the simpler the path, the higher the relative addition of the bug trigger, right? So the shorter the path, the more of the path is going to be the bug trigger. And the shorter the path, the simpler the path. So after simplifying for each crash that we have, after simplifying each crash as much as possible, so simplifying the path to the shortest path possible, we can then cluster by graph topology to match the similar subpath. So for hopefully extracting the subpath sequence that is the bug trigger. This is where we introduce Igor. I'm a huge Terry Pratchett fan. If you've ever read Terry Pratchett's book set in Ankh-Morpork, you may have heard of the Igors. Igors are humble servants to mad scientists, and we felt that this was a fitting name for our tool to call it Igor, because Igor will take all the large amounts of crashes that you give him and distill it and triage the amount of individual bugs that you should actually look at. So you take all the crashes, pass them to Igor, and our system will then do data processing, generate the traces, minimize the paths, and then analyze the different remaining traces, cluster them, and tell us how many individual bug clusters there are. And the goal is to have unique bug clusters. So for each bug, we have one cluster and a set of seeds that map to this bug without to disambiguate the different crashing seeds into unique bugs.
Yes,
yes, go ahead.
So Pranesh asked that the corpus that you mentioned last slide, like 59 years of CPU, you have so many crashes. He asked whether this corpus is available publicly, means from where somebody can get access to these seeds.
Yes, we would be happy to share the corpus. Just shoot me an email.
All right.
Yeah, we are very happy to share this corpus. So just go ahead, shoot me an email, and I'll set you up with a link. It's quite a bit of data, so you cannot really host it, but we are happy to send it using some means.
Yeah. So Pranesh, you got your answer.
So counterintuitively, I've just talked a lot about fuzzing and increasing coverage. Our approach here is to minimize coverage. Now, we take one crashing seed, right? So this seed crashes, and we for each crashing seed, we take it and then we run a fuzzing campaign trying to minimize coverage. And the goal here is, by minimizing coverage, we get rid of all the path components that are not necessary. So we are looking at the path that the crashing seed takes through the program, and are trying to minimize the crash to the shortest possible seed. So based on a crashing seed, we make sure that it always triggers the same bug or the same location, and we get rid of as many components in the path as possible. We keep a seed if the seed does not exercise a common edge, or seed exercises some edges with fewer hit counts. And in this example here that I'm showing, you see the simplified graph. So all the red nodes are no longer visited. So this is a large amount of basic blocks that we were able to remove by only adding a few basic blocks while still crashing at the same location. So this makes the crashing seed much simpler and more concise, allowing us to do clustering in a second step. Now, if you have the minimized version of each of the crashing seeds and you cluster them, you get a much nicer clustering result. in the, like, we've visualized the distribution of 4 CVEs in, I think this is lit PNG. If you visualize the different bugs on the left-hand side, without pre-processing, it's just like a big mess. If you visualize it after our reduction, you get unique clusters between the individual crashes. So this is highly effective. To summarize, fuzzing is great at producing crashes when you use the right sanitizer, but programmers are overwhelmed through the thousands or 10,000s of crashes. Crashes need to be distilled into bugs to be useful. Then a developer can, or an analyst can, figure out what the individual bugs are and start looking at those individual bugs, one bug cluster after the other. Our key insight here was that minimizing the path lengths of seed enables similarity matching in the second step. And then our Igor groups 254,000 crashes across 39 bugs into 48 distinct clusters. So from an analyst perspective, like, we have 39 bugs in our ground truth data set. Igor gives you 48 clusters to look at. So 48 is close enough to 39 that it's viable. 254,000 is not close enough to 39 for an analyst to look at. So we have actually made analysis and triaging of bugs much more, reasonable compared to before. Any questions I can answer regarding Igor? Except for making the dataset available. Please go ahead.
Excuse me. May you return back to the whole architecture of Igor, please?
So it's a two-step pipeline. In the first step,
what is similarity calculator? And my second question, the graph data structure you're using for the big programs, because if the program are big, going with the proper data structure to keep the graph for the particular program is like,
yep. So we extract the execution trace. So we have a sequence of basic blocks that we then turn into a graph.
Mm-hmm.
So it's, in the end, we translate this into a graph similarity problem. And so in the first step, the first square, we pretty much minimize for all the crashes. We minimize the graphs, and then in the second step, the oval shape, we do graph similarity matching to cluster based on that. Does that answer your question?
yeah, and your graph is just adjacent list, yes?
My graph is a what?
Data structure for the graph is just adjustment list, like node and list of nodes where you can go from this node, or you use just common probe data format.
No, it's a simple. It's a very simple graph encoded in Python, like a graph data structure.
Oh, I see. Okay.
If you want to play with the implementation, it's available open source on the website.
Mm-hmm.
Cool. Other questions? If not, let me continue. There's more stuff to look at. Let's say you're creating a new fuzzer. You've changed a couple of features. How do you figure out if your fuzzer is actually effective, if your fuzzer is useful, if your fuzzer is better than other fuzzers? You could use code coverage. You could use number of crashes, or you could use number of unique bugs. Well, code coverage is subjective. It may really depend, and code coverage does not necessarily indicate that you found all that one fuzzer is better than another. Crashes, as we just discussed, are imprecise, And bugs lack ground truth, right? So you would have to find all the possible bugs. Otherwise, you cannot give a statistical measure about the quality of a fuzzer, because you're measuring an unknown quantity, because you only know after the fact that a bug has been found or not. So we need something else. To evaluate fuzzers, we have developed a ground truth framework that we call Magma, that allows you to measure fuzz and compare fuzzers against each other. Our observation here is that ground truth bugs are closest to the main goal for fuzzers, finding as many bugs as possible. And we allow, based on our tool and instrumentation in it, to distinguish between reached and triggered bugs to enable a form of second order comparison for the individual fuzzers. Benchmarks must be diverse, realistic, configurable, and usable. And Magma implements and follows all these properties. So if you're working on fuzzing and you want to evaluate your fuzzer, please use Magma and come up with a great comparison against many other fuzzers that are also in this space. Let's talk about some fuzzing niches and fuzzing techniques and how to go in there. And this is just a couple of interesting topics I found would deserve further attention. And you may see that in a current hot topic is fuzzing embedded systems, which haven't been explored before. Real-world embedded systems are often customized to a certain use case. They are diverse, task-dependent. There's different kind of peripherals that depend on exactly what the chip is being used for. For example, a temperature sensor is only going to be used in embedded systems that are used in diverse environments. Code is going to look precisely for the sensors it expects, so there's no automatic peripheral discovery. Firmwares handle and support only the required peripherals and nothing else. It's very, very complex. A lot of minimized code, minimized memory, minimized small memory, minimized power, and so on. So this is a very different space that's very hard to work with. What we've explored is that on these systems, there's many different hardware abstraction layers that replace the operating system to some extent, making it hard to analyze, making it hard to work with. Like an analyst would have to work for several weeks to support a new embedded system area or a new firmware. This is way too much overhead, way too costly for the large amount of systems that actually exist. And we need something that enables us to quickly analyze and scale to new firmwares. And this is where Hallucinator comes in. If you look at a modern firmware, there's the off-chip hardware at the bottom, on-chip hardware such as MMIO, and then the firmware on top of it. The firmware consists of a hardware abstraction layer that abstracts the low-level functions, which is like a simplified library-like operating system. Then you have a bunch of middleware, such as a real-time operating system, protocol stacks, peripheral libraries, and so on, and application code at the top. This is usually what you want to find all the bugs in. But maybe you also want to find bugs in the middleware. So what we abstract on is the middle layer, the hardware abstraction layer. We want to rehost. We use QEMU at the bottom and then enable high-level replacements to allow you fuzzing the complete firmware by itself. But you can also do high-level replacement and to API compatible the replacements to directly interact with the application code. So we enable rehosting at different level by allowing you to define interaction points at different APIs. So in the end, it's a way to enable HAL-based firmware rehosting, where you're defining a certain HAL, the HAL functions, and then you can run the rest of the firmware in QEMU itself at very high speeds. So QEMU translates the instructions. We trap on peripheral access and enable fine-grained introspection on top of it. I don't know how much you're working with embedded systems, but it's a nice angle to go a bit beyond just what is being run on laptops or desktop systems and go into the embedded framework. It has been quite a bit underexplored until now. And there's also a lot of interesting stuff happening here to go deeper beyond all of the just shallow coverage that has been explored so far. If you want to stay on more modern systems, let's say you want to stay in user space, another challenge that I mentioned at the beginning is to work with binary-only code. Oftentimes you don't have binary, the source code, and you can only work with the binary code itself. Or even in a larger system, some of the libraries may only be available binary only. Retro-write allows you to statically rewrite existing binary code by doing symbolization, translating binaries into labeled assembly, and then providing different kind of instrumentation passes for fuzzing coverage, sanitization, and so on. So you can rewrite existing binaries at zero, and then result in zero overhead binaries where you only pay for the added instrumentation. So this is a zero overhead rewriting mechanism that allows you to do fuzzing for embedded systems. I will keep this short, not for embedded system, fuzzing for native binaries with support for AR64 and X64. If you're interested in this, I can go into more detail later, but I want to leave a couple of minutes for questions. So if you're interested in binary-only rewriting, we can get back to that later. But I do want to spend 2 minutes on some of the unsolved challenges in fuzzing that I would be also interested in hearing your thoughts on. Fuzzing is maturing. We've had 60, 70, 100 papers at top-tier conferences over the last couple of years. What's next, right? This is not by no means a solved problem. A couple of interesting challenges that I'm thinking about is defining metrics for starting seed corpora. A lot of the research work assumes that you start with empty seeds, but in reality, an analyst would spend a couple of minutes or hours even to procure a good set of starting seeds, enabling the fuzzer to explore very quickly and find other new areas. How can we define such good seed corpora and how can we generate them? Another angle is cross-distillation. How can we reuse seeds among different targets? Going from let's say, fuzzing drivers on a Windows box to fuzzing drivers on a Mac OS box. Not a problem. Stateful programs and network protocols are very much underexplored so far. Handling peripherals in embedded systems. Helping the developers analyze discovered crashes and distinguishing exploration and exploitation phases. All of these are different interesting challenges that are coming up that we may want to talk about in a bit. So let me conclude. I'm calling on you to start riding the fuzzing hype train. Join us and help us harvest as many bugs as we can. Bugs are everywhere, and the fuzzers provide support for different kind of ways for developers to find and fix as many bugs as possible. They are well integrated into the development toolchain. Good fuzzers leverage coverage feedback to find crashes, and good feedback and mutations are also program dependent, so are more and more involved. And we have to define ways how we can get this involvement going on. Future research will focus a lot on usability, reducing the startup cost, seed collection, seed generation, specializing fuzzing to new environments, and helping developers make sense of the bugs by giving them additional information and details. And this is all what I wanted to present. According to my clock, we have 3 minutes for some more questions. So thank you for your attention, and please shoot away with the questions.
Thanks. And I know we are online, but yeah, thanks, speaker. And if you have questions, either you can raise your hand or maybe you can write.
I have one question. I want to go back to the Igor architecture. And so you talk about, so what you were saying is you generate a graph, and from the graph, you do other stuff, and you talk about the similarity graph operation. And I would like to know which algorithm are you using to do the similarity graph? Yes, that one.
The silhouette score.
Yeah. So I was talking about the similarity graph operation, and I was wondering which algorithm you are using to do the similarity graph.
Oh, that's a very good question. I would have to go back to the paper. We use a standard machine learning and graph comparison library for both the. I'm not a machine learning expert. I'm not a graph comparison expert. We use standard tools. I'm sure we declared it in the paper, but it's nothing fancy. So if you come up with something that's fancier and has better results, please let us know.
Okay.
It's a very good question. I'm not an expert in that. We use the standard Python libraries for that.
And staying here, I'd like to ask yet another question, which is in my mind, I think it's pretty obvious here. It's control flow, and we're speaking about the crashes, which means we're interested in some part of data flow. And maybe what do you think about not only the control flow graph constructor, about the data flow constructor also, because I think you are familiar with the work we got about the code property graph, which combines some data and control flow, because all the crashes is more or less it's about data.
Yeah. I agree very much with you. In an ideal world, we would have that. We tried different kinds of data flow approaches. So we did try to run the programs under libdft to have a simple data flow approximation. Just didn't scale. Like we didn't manage to run it on the large amount of crashes we had. So I do like your point. There's likely something there for data flow. There is a case for data flow that we could likely make this simpler. We did try for this project. We didn't get to reasonable results because it was too much overhead. Now, let me also tell you about a failed research project, the project that we had. So we had an initial hypothesis that we can replace code coverage with data flow coverage as a feedback for fuzzers. And we actually implemented a full data flow framework that collects data flow coverage, gives feedback to the fuzzer, and worked really well. And we actually thought that we had good results on that. But then when we evaluated it against control flow fuzzers, we found that the granularity of the data flow that we had for the vast majority of programs was less precise than the control flow coverage. So as it turns out, for the majority, and this is unfortunately not published because it was a negative result, but as it turns out, for the vast majority of programs, the control flow is a superset of the data flow that you'll get. So data flow is always subsumed by control flow for the majority of programs. Now there are exceptions. For example, different kind of like very aggressive XSL processing or something. They are an exception. But for pretty much all the other programs, we found that the control flow is just the better metric to look at this. Now I'm still thinking of how we can publish this and make this available to the community, because I think this is a very interesting results and also very counterintuitive. Yeah, but very good question. Thank you.
I have one question related to hallucinator. So when you are describing that, you wrote somewhere that higher level abstractions implemented in Python, which are kind of where it goes to out of peripherals. So these are you kind of manually encoded them, or there is like kind of some sort of automated analysis to find it should be extracted in?
I likely went way too quickly on that. So the idea is, if you look at embedded systems and embedded system platforms, there's 80,000 different peripherals. There's on the order of 20, 30 commonly used device types that share similar HAL interaction patterns. Now, our idea was to provide Python implementations for all these 20-ish different HAL types, and then intercept, right? There would be two approaches. One approach would be we emulate each of the 80,000 different peripherals and emulate every single memory read, memory write, and then model and abstract the actual peripheral as it is being used, and have a like an implementation of this peripheral, right? An emulation of this peripheral. This is way too complex and would not scale. What we did is we emulated at the HAL API, which is common among all this, pretty much among all the common the instances of the same type of peripheral, for example, for a network card, right? So we only need to implement one network card, send packet, receive packet. And we implemented the state in Python, making it much simpler. So if you want to support a new type of peripheral, you can just add a new Python function, then the HAL interaction point, interception points, and then infer them as is. Now, the key question becomes, how do we figure out where these HAL interaction points are in the firmware? And for that, we have developed an approach that we call lit match. Think of it as flirt signature, where we detect, if you're familiar with IDA, like flirt signatures where we detect where these interactions actually happen. Did that answer your question?
Yes. Okay, so I think we are already running out of time. So if there are other questions, you can also, I think, mail directly to Mathias, I guess, or otherwise you can also send us. We will try to get answer from Mathias. And so let's thank the speaker once again. Thank you, Mathias, for such a nice
thank you very much.
Talk. Yeah. And yeah, thanks a lot, everyone.